Okay, great. Yeah, welcome everyone to good morning and good morning and welcome to our machine learning technique workshop. I just wanted to spend a few words quickly on how it got together and thank a few people. So first, thanks you all for coming and showing interest. It's really great that so many people share the interest and have signed up. The idea really came together in one of these CUBRIC kitchen chats. Matthias, who is a postdoc in Penny Lewis lab, is based in our wing, and we started talking about possible data analysis techniques, and then at some point it became clear that he actually knows what he's talking about, and he actually is also the author of a toolbox for machine learning, of which we will learn more later today. So we thought, well, with Marek, why don't we put a workshop together and provide some training between ourselves, and then also give people who actually already work with these techniques in CUBRIC sort of a platform to present their work, and then also to network with each other. So that's the idea. Derek was also in the kitchen, luckily, and he generously provided the funding for today. So we'll have some lunch later, and biscuits are outside. Just a quick overview of today. You've probably seen the schedule already. So we will start with a general introduction by Matthias, and then to the topic of machine learning, and then Jiaxiang will, after the coffee break, talk about particular challenges that come with neuroimaging data. Then Matthias gives us an overview, sort of a demonstration of his toolbox, and after that we'll have a lunch break, and then people from CUBRIC will present their work, and at the end we have an open discussion table. So that's an opportunity really for you to bring up questions, but also where we can discuss where we want to take this next, what you would like to do with machine learning. Cool, so before Matthias starts, Marek will now give you an overview. Marek has been mainly responsible for the logistics behind the workshop. So thank you, Marek, and your floor is yours, and here's the pointer.
Yeah, so just a few housekeeping details. Thanks, David, for introduction. Yes, we're going to have an open discussion, and if you have any points you would like to raise during this discussion, please feel free to write them on the sheets of paper put at the table on the right-hand side of the door. They're right there for you all the day, and we will go through them before the discussion. Next thing, as we're having this all registered on a video, and the video will be, at least the screens are video registered, and the recording will be released. If you ask any question, and if you don't want to be on a recording, please tell us, so we will cut off your voice. It's just to let you know. Yep, in terms of this hands-on workshop, it's quite a lot of people, far more than we expected. So we unfortunately probably would not be able to provide the power plug for everyone. So please, if you can, try to work on your laptop on a battery. And one last thing, there is a lunch and a poster session. So lunch will be provided in the hall outside. As the poster session begins at 12:30, you might want to hurry with grabbing your lunch before all the people come and eat it. That's all. Have a nice day. Enjoy. Thank you.
All right, so also welcome from my side. First of all, I should apologize in advance. I got a tooth root infection which got really bad last night, and I'm only here thanks to a generous supply of painkillers by Cas. So please bear with me if I'm not 100% focused. I'll try my best. How do I? That's it. Yeah. So maybe a few words about the setup. So in the morning session, the idea is basically to lay the foundations. So we'll be talking mostly about classification and machine learning on a kind of theoretical, conceptual basis, and really fancy, interesting stuff relating to brain research is what we see in the afternoon. So also my talk is, if you are experienced with machine learning, it will be very basic, and I was told I'm not allowed to put too many formulas there, so I'll mostly use pictures. And there's a few formulas, but they're usually quite simple. Okay, so let's get started. So the first thing I would like to mention is or answer the question, what actually is machine learning? And I guess there's different definitions of what it entails, but in my opinion, there's basically 3 pillars to machine learning. The first one is reinforcement learning, and that's maybe the fanciest one, but the one that's for us probably the least interesting one. That's the one that's used in AI, for example, in robots. And it's a complex algorithm which basically implements the interaction of for example, artificial intelligence with its environment. The second branch, which is more relevant to us, is called unsupervised learning, and it includes methods such as k-means clustering, spectral clustering, but also PCA and ICA. Here the idea is basically that you get a big bunch of data and you have very little information about it. And you can use these methods to actually squeeze out some information out of the data. And the third topic is the topic of my talk now, is supervised learning. And supervised learning has 2 sub-branches. One is regression, which you're all familiar with, and classification, which is actually the focus of the talk. So in classification, we have some data, but we also have labels to the data. So usually it's 2 or 3 different classes. And what we want is, in the end, to build a classifier which can predict the label given the data. And in the course of this talk, we will learn about a few methods of how we can achieve this. Before we start, I'd like to have a slide on some terminology, just to be sure that we all mean the same when we're using these terms. And this is basically my definition of what these terms mean. So you often hear the term decoding in the cognitive neuroscience community, and I would say this is what like the rest of the world calls classification. So usually the idea is here we want to predict we want to predict brain states or experimental conditions given a set of brain data, which could be activation in voxels or structural data or EEG data. Multivariate pattern analysis, MVPA. I haven't really seen a definition of it. My personal definition is that it's kind of an umbrella term which includes both classification but also methods that build on it and extend it, such as RSA. And finally, a few important terms when it comes to classification. So first of all, what's the goal? So the goal is we want to predict some output variable, which is usually categorical. Unlike regression, where the output variable is continuous, given some input x. So that's the most general view on classification that one can have. And in machine learning, these variables have particular names. So this output variable y that we want to predict is usually called a class label. So it would be in regression, you maybe come across the term response variable or dependent variable. And features is actually the set of variables that we use in prediction. So if you would have a regression model, you would probably call it predictors. Or in classical statistics, it would be called independent variables. But in machine learning, we use the term features. And basically, a classifier is nothing more than an algorithm, or sometimes just a simple mathematical function, which maps from features to class labels. So you could say it's a function f, and we put in some x, which in the context of brain research would be some brain data, and we want to get some y out, which would be a class label. And to make this a little bit more concrete, I just want to mention two possible examples about what features and class labels could be in the context of brain research. So one possibility would be, for example, you have a structural MRI data and you have gray matter density for, let's say, 100,000 voxels. This is your features. So it's a large data set. You have 100,000 variables, and you want to predict, for example, whether the brain belongs to a person who's a patient with a particular condition, or a controlled subject. Another possibility would be, for example, you're measuring MEG activity while people are watching images, And these images could be, for example, living or non-living. So in this case, the task of the classifier would be to take the MEG activity at a particular time point, let's say 300 milliseconds post-stimulus, and just using this activity predict whether the subject has seen a living or a non-living object. Okay? So, once again, let's zoom in a bit on the difference between supervised learning and unsupervised learning. So in supervised learning, as I mentioned before, we have data or feature vectors, and these colors here, they would usually represent some kind of numbers. So we would have these samples, and we'd also have labels. And many classification problems are binary, so we have just two classes, and then often the labels are coded as +1 for the first class and -1 for the other class. And usually the approach is that we have some training data where we have the labels, the labels and also the features, and we train a classifier based on that. And then we validate the classifier on new data where we don't have the labels. And here the idea is to actually predict what the labels are. In unsupervised learning, we are basically stuck with only the feature vectors. So we just have this bunch of data, and we don't have any labels. So ideally, we would want the algorithm to provide us the labels from scratch, which is, of course, a much harder problem. So let's look at this a bit more concretely. So in an unsupervised learning problem, this is a very simple one. We just basically the circles here are our data points. So they have an x and a y coordinate. So it's a two-dimensional problem. And clustering would be actually turning them into groups. So we could say, okay, these ones, they're relatively close to each other. Maybe they form one group. Maybe the other ones form another group. This could be an example of, for example, k-means clustering. But of course, there might be also three groups. So maybe there's another blue group. So already with clustering, at that point, you have to insert some knowledge usually into the clustering algorithm. You can try without, but usually it's better if you insert some knowledge. Whereas in classification, the task is a little bit easier because we already start with training data that has been labeled. So we already have the colors. In this case, it's two classes, a red class and a green class. And the idea here is to separate the spaces into a space that belongs to the red class and a space that belongs to the green class. So, for example, LDA, linear discriminant analysis, would try to find a linear hyperplane. So in 2 dimensions, it's just a line that separates the two classes. And as you see, in this case, it's even not possible to, you cannot draw a line that perfectly separates the green and the red dots in this case. But basically, we would say that any new data point that falls into this part of the image would be red. Any data point would be green that falls in this part of the image. Support vector machines, which we'll also get to know a bit later, are more flexible. So they can have decision boundaries which are nonlinear. They can better adapt to the data. And then, of course, if we have a new data point, this could be the new circle here, you can already appreciate that these two methods would give different answers, right? LDA would say that this is a green data point, whereas support vector machine would say that this is a red one. And the question is that actually, is support vector machine learning the right structure, or is this maybe an outlier and it shouldn't be there because we always have inherent noise in the data, right? So this is a really tricky problem. You don't want your models to be too complex and to adapt to the noise. And maybe another view on machine learning was put forward by Leo Breiman, a famous statistician who also invented the random forest. And he said that basically in both machine learning and classical statistics, we're interested in the relationship between some input and some output. And we think that there's some natural process mapping the input to the output. And in the classical statistical approach, we would have a kind of model. So we say, okay, we think the relationship between x and y is linear. So we use a linear model, or logistic regression model, or Cox model. Whereas in some machine learning approaches, like neural networks or decision trees, we're not interested really in that model. We just kind of circumvent it. So all we try is to get a model that predicts y well from x, and the model itself doesn't need to represent the structure of this natural process. Actually, in reality, many of the methods that are used in machine learning actually also fall in this case. So we'll actually talk about linear discriminant analysis and logistic regression, which we also use for machine learning. So this, I think this dichotomy doesn't completely cover machine learning. Okay. Maybe lastly, just to kind of pit against each other, the univariate, more classical approach to statistics, where we would look at single sensors or voxels. So the advantage of that approach is that it's specific. So if we find an effect in one voxel, we know that it's located at this voxel. And also we can identify predictive variables very easily. This is actually not so interesting. So in the multivariate approach, we can use groups of sensors or voxels, or maybe all of them. We could, put 100,000 voxels into our model. And thanks to that, we have a higher statistical power, and also we don't have a multiple comparisons problem because we just do one prediction at once using all of the data. And well, a disadvantage, which is not mentioned here, is that it sometimes can be unspecific. So it's sometimes harder to identify the variables that are predictive because you're using all of them at once. And the nice thing is that machine learning methods often find latent variables, or sometimes even implicitly transform the data into source space. So shown in a Neuroimaging paper that, for example, linear discriminant analysis is actually formally identical to LCMV beamforming. So there's actually tight connection between linear classifiers and inverse methods. And you often find that linear classifiers actually identify brain sources. Okay, so let's talk about classification. And let's start with a quote, which is sounds maybe trivial, but it's kind of important. So basically, all models are wrong, but some are useful, and I think that's a great motivation for using linear methods, because we all know that in most natural processes the relationship is not really linear, but still it's quite useful to use a linear model, because in many cases it's a good enough approximation, and linear models are very well interpretable. So in the next slides, I will basically cover an approach called the Bayes classifier. Then I'll talk about 3 linear methods: linear discriminant analysis, logistic regression, and support vector machines. And I'll cover some nonlinear methods such as kernel SVM and random forests. Okay, let's start with the Bayes classifier, which is really a kind of ideal world approach, where let's just imagine for a moment that we have an infinite amount of data. We have infinite computational resources. So in that case, what classifier would be the best one? Well, the Bayes classifier actually, so in this case, if we have an infinite amount of data, any point in our data space, we have seen data at each point in our space, right? So if you get a new unlabeled data point, what the Bayes classifier would do, it just looks at this data point, how often have I seen, or what's the proportion of samples from a particular class I've seen. So for example, if, I don't know, 60% of the samples are from the blue class at this point, 40% are from the red class, the Bayes classifier would say it's the blue class. And the nice thing about the Bayes classifier is that it's the lower bound for the error of any classifier. So you can never be better than the Bayes classifier. Of course, in the real world, we don't have an infinite amount of data. However, if you do simulations, you actually have the information, because you simulate the data about the true density of your data, and you can compare classifiers to the kind of ideal classification rate that you would get with the Bayes classifier. So this is basically a 1D example where we would just have one feature on the x-axis, and the red line is the density, or the probability that we see a red sample, and the blue line that we see a blue sample. So basically, if we get this data point, the Bayes classifier would say it's the red class. Here we would say it's the red class. He would probably randomly choose one of the classes, and here the classifier would say it's the blue class. Very simple. Okay. And this is basically a two-dimensional example, the same idea, where we have yellow and blue data points, and the dotted line here is actually the decision boundary that the Bayes classifier would give us. All right. So in the real world, we don't have infinite data. Our data space looks more like that. So it's a bit like the real space. So it's mostly emptiness, and there's a few dots here and there, and we got to work with that. The reason I introduced the Bayes classifier is because some of the classical methods, they actually try to mimic it. One of them is the k nearest neighbors approach, which says, let's say we get this new data point here. So we've seen the yellow data and the blue data points before. We get a new data point, and we don't know if it's yellow or blue. And k nearest neighbors would say, well, I don't have information about this part of the space, so I just look around I just look what do the closest neighbors say. So if I look within the circle, there's 2 blue samples, 1 yellow sample, so it's most likely that this is blue. So this is how k nearest neighbors works. And on the right side, you basically see how k nearest neighbors would partition the space into in the blue part and the yellow part. And this is the formula. I'm not going to go into that. So we can just look how does the decision boundary look like for k is 10. So k is 10 means for each data point, the classifier looks at the 10 nearest data points around and looks which class has the majority and chooses that as the target class. And the dotted line again is the Bayes classifier. So this is simulated data, so we know the truth. And the black solid line is k and n, and you see that it does a pretty good job. So it's very close to the ideal, to the best you can get. And here you can appreciate a bit more what happens if you change k. So if you set k to 1, basically each data point is mapped to its one nearest neighbor, and you see that you get a very jagged line, and you even get some odd things happening. This is clearly overfitting. So these points are probably noise. So the classifier is kind of overfitting to the data. On the right side, if we take too many neighbors, you see that we almost get a straight line. So this is a case of underfitting. So it's of course an art. It's of course an art to find the right k. And what is shown here on the x-axis is basically, well, it's a bit weird. If you go from right to left, we are increasing k, and the yellow line is the test error we get on new data, and you see that there's a sweet spot. And here the dotted line is again the ideal Bayes rate. So you can see that for a particular choice of k, you get very close to the ideal, to the best you can get. So having seen that, KNN is a simple and powerful classifier. It makes very few assumptions on the data. We can actually use cross-validation to estimate the best value of k. So we're done. I mean, if that's the best we can get, we could stop the lecture here. But of course I don't. So what's the problem? So actually KNN works very well in small dimensions. If you have 1, 2, 3, 4, 5 dimensions, it works well. In high dimension feature spaces, it collapses and it doesn't do a good job anymore. And one of the reasons is the kind of curse of dimensionality, because in high dimensional spaces there is no really neighborhood. So if you imagine that each of your feature has a value between 0 and 1, your feature space is a cube, or in high dimensions a hypercube. A hypercube in 100 dimensions has 2 to the power of 100 corners. So there's much more corners of your data space than even data points. So basically in high dimensions, the space is always sparse. You always have too little data. So you need more powerful models which have more, where you kind of insert some extra knowledge. So let's turn to linear classifiers. So Actually, we've just talked about the Bayes classifier, and I'm sure you all know Bayes' rule. So we can the Bayes classifier uses the posterior probability of the class given the data, and it always chooses the class that has the highest posterior probability. And using Bayes' rule, we can rewrite it as the likelihood times the prior divided by the normalization term. And actually, okay, I've just said that. So f is here the density function, pi is the prior probability. And so if we would know f and pi, we could directly use Bayes' theorem, but of course we don't know it. But this is the starting point for LDA. So what LDA does is actually trying to estimate these two quantities. So the prior is estimated as the fraction of training data belonging to class J. So for example, if, this is an example. Let's say we have 100 participants, 20 patients, 80 controls, then the prior probability for a patient would be 20%, and for a control would be 80%. But in practice, sometimes this is not desirable because in your experiments, these fractions can be quite arbitrary. So in many practical cases, the prior is set to like 50% for 2 classes or 33% for 3 classes. Yeah, that's what I just said. So the more interesting part is actually the density function. And that's very difficult to estimate. And LDA just makes some very strong assumptions on it. And there's 2 key assumptions. First of all is that LDA assumes that the classes are normally distributed, so they're multivariate normal distributions. And the second assumption is that for each class, the covariance matrix of this normal distribution is identical. So that's a very strong assumption. So how does this look in a kind of picture? So let's imagine we have again a 2-dimensional example, feature 1, feature 2. 2 different classes. So what LDA would basically do is estimate the class densities using multivariate normal distributions, and this is what you see underneath here. So now the z-axis is the probability density, and LDA maps the data to these kind of distributions, and then performs the classification using the information of these distributions. A different perspective we can take towards LDA, and this would actually be called Fisher's discriminant analysis. It turns out to be the same for 2 classes as LDA, is that we actually look for an ideal projection of the data. So let's say we have these 2 classes of data points, one again the blue class and the red class. We can look at the densities of those. And then we can see what happens if we project these 2-dimensional data onto 1 dimension. Let's say we project it on the x-axis, and we just look at the amount of data we get at each point on the x-axis. Would look like that, right? So you see most data is in the blue class is centered around here. So if we project it on the x-axis, we'll find that most likely the data is here, the red data is here. But you see that they are not very well separated. Right? So let's try to project it on the y-axis instead. And again, you see that they are not very well separated, these 2 distributions. We can do something very stupid, namely fit a linear regression line and project it onto the linear regression line, which does an awful job. But you can imagine if you can play around with this line, and if you just shift it around, there should be a particular projection which is ideal. It would be something like this. So there's a projection where we find that the means of the 2 classes are separated as far as possible, and at the same time the variances within the class are as small as possible. So this is Fisher's discriminant analysis. And again, for 2 classes, it's identical to LDA. And in the end, it's achieving the same as we've motivated LDA from the Bayesian approach. Okay. So another method, another linear method is logistic regression, and here we actually directly model the probabilities of the classes. So we kind of have a generative model for the posterior probability. that the class is 1 given some data x. And I'll not go into the details of the model. Basically, it's a general linear model. So just shortly mention that it's linear in the log odds ratio. So if you compare the probability that we see class 1 divided the probability that we see class 2 and take the log of it, it's actually a linear model of that. And to get more of a visual impression, let's imagine we have just one-dimensional data. So the yellow points are the data points, and if the y value is 0, they're in the first class. If the y value is 1, they're in the second class. Basically, what logistic regression does, it fits this logistic function such that the values for one class are most likely 0, the values for the other class are most likely 1. If we can also look at this in 2 dimensions. So we've seen this example before. And again, what logistic regression does, in this case, it fits a logistic plane through the data. Again, it tries to map the red data points to a probability of 1 and the blue data points to a probability of 0. Okay. Marek, how many in the time?
Yeah, you have like almost 30 minutes left.
Okay, perfect. So I can go a bit slower, I think. So let's turn to the third.
Oh, sorry. No, 15. Sorry.
15 minutes left?
15 minutes left, yeah.
Okay, then I have to hurry up, I think.
Sorry.
Faster, not slower. Okay, let's talk about the intuition of support vector machines. So let's imagine we have these 2 sets of data points, the blue ones and the red ones, and we want to separate them, again with a linear classifier. So basically we want to fit a line. Actually, what I want to do now is so there's 3 different possibilities here, and one of them is, well, some of them are better than others, and I would like to ask you what you think. So could you please raise your hand who thinks that this is, just by intuition, the best hyperplane? Nobody. Who thinks that this one is the best one? Could you please raise your hand? Yes. And who thinks that this one is the best one? Okay, nobody. So I think it's pretty clear. We've got 100% for the second line. You actually all did just intuitively what support vector machine is doing explicitly, analytically, namely the following. The idea is that you don't just fit any plane, you fit a plane that has the maximum distance to its neighbors. So the way you can think about it is you fit in a hyperplane and it's inflatable. So you start inflating it until it hits the first data points. And you want to, and this is called the margin, so the width of the hyperplane, so to say. Well, it's not the hyperplane. This is the hyperplane, and the 2 dotted lines are called the margin. And basically, SVM is a maximum margin classifier, so it tries to blow up the margin as much as possible. And it blows it up until it hits some data points in this case. And there's 3 data points here, and these are the support vectors. So if you hear a support vector machine, what are support vectors? That's the ones, in this case, that sit on the margin. Well, what's the problem with that? So we've seen this example before. Let's add 1 data point here, namely the blue one, and see what happens to the hyperplane. It just flips over right away. And it doesn't look that good anymore as well. So it kind of over-adapts to the data, right? So this is one problem. The second problem is, in this case, we can't really fit it anymore because we can't really separate the data. So this is the kind of hard margin classifier, doesn't take us very far in real-world problems. So what is done in support vector machines is introducing a soft margin, which means that you don't want to separate the classes, you just want to almost separate the classes. So there's some variables introduced that are called slack variables, and they basically allow for a violation of the hyperplane or a violation of the margin. So this is obviously more robust to outliers, because if we have an outlier, we don't need to care, because we have a slack variable that takes care of it. And obviously it's called soft because we allow samples to penetrate the boundary and be on the wrong side of it. And in this case, we have a so-called hyperparameter, C, which sets the total amount of violations that we allow. And this is just a visual impression of same data set, the same SVM, and basically what happens if we change the hyperparameter C. So if we start here, we allow for very few violations. And what you see as we increase, as we decrease C, first of all, the margin gets wider because we allow for more violations. We can include more samples. And more importantly, you see also the angle changes. So basically, in this case, the angle of the line is very much adapted to the samples, which are very close. Whereas in these cases, it's kind of, well, it's integrating across much more data, which makes sense because then we are less susceptible to outliers, which are very close to the hyperplane. Okay, so we've talked about linear classifiers. Let's go to nonlinear classifiers now. And to motivate this, let's look at this problem where we have the red class in the middle and the blue dots on either side of it. Obviously, if you fit a linear classifier, that's about the best we can do, which is pretty bad. So it doesn't get us far in this case. So we need something else. And to motivate what the approach is that SVM takes is, let's imagine the following situation. Very simple case where we have a one-dimensional data set. So yellow and blue dots, and we want to separate them. In one dimension, separating them means just defining a threshold. For example, here, and you say everything left of this threshold is the blue class, everything right of it is the yellow class. And you can see there's no threshold that separates them completely. So what we can do is actually, let's just add a second dimension to it. For example, we don't just take the x value, we also square the x value and plot it as a second dimension. And then it becomes a parabola. And in this two-dimensional space, we can actually fit a line, right? So we can fit a line through this parabola, and everything above the line is the yellow class, everything below the line is the blue class. So we've just started with a problem we couldn't solve. We transformed it into a higher dimension, and now we can solve the problem. And what you can do with SVM then is to map this back to the original space. And the original space is actually the gray line here. And you see that the hyperplane intersects the original space at two points, here and here. So if we map it back to the original case, these are the two intersection points we just had. So basically the classifier would say everything left of this threshold is yellow, everything right of this threshold is yellow, everything in between is blue. So we get a perfect separation. That's almost what support vector machines do. There's more to it. This is a bit mathy. I'll skip this for the sake of time. So this is the heart of, the kernel trick is the heart of the support vector machine. Basically, the idea is that, I'm sorry, this is a little bit technical. So basically, we have a map, a feature map, which maps our data from the original space into a higher space. We've just seen an example mapping the data from 1 dimension to 2 dimensions. And a support vector machine operates by mapping this data into a high dimensional space and then calculating the dot product. And these brackets represent the dot product in this high dimensional space. But the cool thing is about support vector machines is you don't really need to go into this high dimensional space. There's a function called kernel function that allows you to do the computation in the original space. So you, instead of mapping into a 1 million dimensional space, you just do the computation in the original 100 dimensional space. You can even implicitly map the data into an infinite dimensional space, which you get if you use a radial basis function kernel. So you wouldn't even be able to explicitly implement this. But with the kernel, you can do the mapping. Okay. 5 minutes. Okay, so let's go back to this example, and what we've seen is that we cannot linearly separate these two data points. What I want to show you now on the next slide is if we use two different kernels and we just see what SVM does and how it looks like in the original space. So one kernel is called the polynomial kernel, and we see that in the original space we kind of get two hyperplanes or two decision boundaries. One is here. Again, the dotted line is the margin, and the other one is here. And you see that it very well separates the two classes. The other one is called a radial basis function, or a Gaussian kernel. It basically defines kind of an inner and an outer class. So this class is basically encircled. So this is the decision boundary. Everything inside the decision boundary is the red class, and everything outside is the blue class. So I just quickly want to mention a few other classifiers. I'm not going to go into much detail. One is decision trees, which are very simple. Basically, you consider each feature separately. For example, you take the 100th voxel, and you classify by defining a threshold on that voxel. So if the value is larger than 1.1, which is arbitrary in this case, you go to the right, and then you consider another voxel. And if the value is smaller than 0.1, you say that this sample belongs to class 1. If it's larger, it belongs to class 2. And the smartness in the algorithm is, of course, the choice of the feature. So which feature do we have to choose, and what's the correct threshold, and how many branches do we have? And the nice thing about the model is that it's really highly interpretable. So you can easily see what's done at each stage. You can, so you can really look inside the model and interpret it very easily. But sometimes it lacks performance and robustness, so it's not that much used in modern machine learning approaches. Let's skip this for the sake of time. I just quickly want to mention random forests. And the reason I introduced decision trees is because I wanted to introduce random forests, which is just a collection of decision trees. So a random forest, basically the idea is that instead of one decision tree, you got many, maybe 500. And there's another very neat trick, is namely you train different decision trees. If they all see the same data, they will all look the same. So you don't want that. So what you do instead, you randomly select subsets of your training data, and you randomly select subsets of the features for each decision tree. So in the end, what you get is a lot of decision trees which pick up on different information. And so how do we classify here? What happens if we input new data, we kind of shove it through all of the decision trees, and they all give different answers, and in the end we cast a vote. So the class that has been most often voted by the decision trees, that's the prediction that the random forest makes. And yeah, neural networks is something that we would need to devote a separate workshop to. So I'll just have this one slide. I'm aware that there's neural networks, but I'm not really going to talk about them. We've talked about classifiers. We didn't really talk about how we measure the performance of a classifier. And I'm going to skip this. So the simplest way to measure the performance is to look what are the class labels that the classifier predicts, compare them to the true class labels. Because if we have our neuroimaging data set, we know the true classes. And we can just look how much do the predicted classes match with the true classes. And then we get a percentage. For example, 70%. There's a 70% match between the prediction and the truth. That's one way to go. And another way is, this is a bit more complicated. So RSC curves, basically the classifiers, linear classifiers, they don't only give you a class label as an output, they also give you a continuous value, which is something like the confidence, you could say. Or some classifiers also give probabilities. So instead of just calculating the classification performance, you could look at the... So basically what a classifier does is it ranks, or a linear classifier does is it ranks the features across the real line. So basically, for these two samples, the classifier would be have a high confidence that it's the yellow class. For this one, it would have a high confidence that it's the blue class. And for these ones, it wouldn't be very confident. And the way you plot the ROC curve is basically you define a threshold, that's the red line here, and you move it. So if you move it to the left, and you look what's right of it, there's one yellow class, one yellow sample, and that's correct, because on the right side we have the yellow samples. So in our plot, we go one step up. So in this ROC plot, we plot the false positives on the x-axis and the true positives on the y-axis. So if you go one step further, we again make a correct decision, right? So we go up one step. Now if we go one step further, we make a mistake, because on the right side we shouldn't have the blue class, it's the yellow class. And we make another mistake, and well, you can see the mechanism, right? So if we go all the way to the end of the data, we basically trace a curve starting from the bottom left, going up to the top right, and this is called an ROC curve. And a measure that's actually extracted from these ROC curves, it's a very useful measure. It's called AUC. It's called the area under the ROC curve. And basically, if you have an ideal classifier, it wouldn't do any mistakes. So the area under the ROC curve would be 100%, right? It would cover, so this whole blue box would be covered. If the classifier would be just guessing, we would randomly go to the right and upwards. So in the end, we would end up with 50%. In most real-world cases, it's somewhere in between. So this is just an alternative measure to measure classifier performance. It's one that's more popular in machine learning, because it's not dependent on the threshold that your classifier sets, because you use all of them. And I think, this is two important concepts I have to mention. Do I have a bit of time?
Yeah, I think we can cut down a bit with the coffee if that's okay, and then, yeah.
Okay. So, because there's two important concepts on these two slides. One is the concept of overfitting, and this plot is a bit complex, so let me unpack this for you. So let's imagine we start with these data points here, the circles, and what we'll do is we'll fit regression models to it, and we add more and more polynomial terms. So if we just fit a regression line, you see that it's not such a good model. And this is underfitting. So basically our model is too simple for the data, or the data is too complex for our model. And by the way, the true model here is the solid black line, and the deviation from the model is some noise. So this is always the case, right? We assume that we have a true model which is noise-free, but everything we measure comes with noise. And so what you see is the blue line actually does a quite good job. So it's pretty close to the real model. And there's a green line, which is very wiggly. It doesn't look that good intuitively. But if you look at, for example, the R-square, it actually explains the data better. So if you just take the R-square as a measure, it seems to be a good model, but it wouldn't perform very well on new data. So this is the case of overfitting. So we see that this model follows the noise in the data, and it doesn't follow the true underlying model anymore. Okay? So that also means if we have a data sample, just looking at the classification performance or the R-square on that sample doesn't give us a good impression, doesn't give us a good information about how good the model really is. So to test the predictive value of a model, we actually have to look at new data. So we train our model on one set of data, and we test it on new data. However, usually in neuroscience experiments, we cannot just go and collect 20 new subjects to test our model on. So usually a more efficient way to go about this is to take your data. So that's this bar is representing your whole data set, and you basically split it into small parts. And let's say you define this part of your data, the blue one, and you just keep it out for now. And you take the gray part and you train your model on this part. But then to measure a classifier performance, you actually use the blue part. So you estimate it on data that the classifier hasn't seen before. So this way you can avoid, or you can control for the overfitting. And what you do then is you repeat it for each of the data sets that you have. So in the second case, you would train your model on this gray part of the data, you would validate it on this blue one, and so on. So in this case, you split the data into 5 folds, and this is called 5-fold cross-validation. If you split it into 10 folds, it's called 10-fold cross-validation, and so on. And basically, in the end, you have used all of the data for testing, and you have also used all of the data for training, but you haven't overfitted to your data. So it's a kind of very neat way and a very economical way to make use of a limited amount of data. And yeah, so this is almost the last slide. So just to sum up, classification allows us to predict classes. We've seen that k-nearest neighbors and linear discriminant analysis actually try to mimic the optimal approach, the base approach, but KNN fails in high dimensions. Logistic regression directly tries to model the probabilities, the posterior probabilities of our classes. SVM has this very nice, neat kernel trick by which it solves nonlinear problems. And we've also briefly seen 2 common measures of performance, namely accuracy and area under the curve. And this is an important take-home message. You should always use cross-validation to estimate the performance, to control for overfitting. And if you want to read more about machine learning, these are all a little bit mathy, but these 2 are, people call them machine learning Bibles. They're really good books. This one is a bit more introductory, and the cool thing, these 2 are actually freely available, so you can even just check them out on the internet. And that's it. Thank you for your attention. So, do you have time for questions? Or?
Yeah, shall we maybe one
question?
If there's one question. Yeah. Otherwise, in general, we can collect all your questions, and we can then discuss them at the open table discussion, and can also collect questions and send around the answers after the workshop. Okay.
There's one in the back, yeah?
Yeah, I was just wondering, when you do the cross validation with 5 volt, do you get 5 models, or how do you? Because you train your model on one step and then on another step.
Yeah, that's a
parameters?
Yeah, that's a good question. I didn't actually say this. Yes, you would get 5 different models. So you train a classifier here, you get a specific classifier, train on that model, you validate it here, and you retrain the classifier from scratch here, and you do it 5 times. So yes, you have actually 5 different classifiers trained on different data sets.
And which one you choose? Do you average the parameters of the model?
Well, in the end, what people sometimes do is for example, they use cross-validation to estimate some hyperparameters, like this C parameter we've seen in SVM. They do this cross-validation, and then in the end, when they found the best parameter C, they train the model again on using all of the data, and then maybe they use it for new data, new incoming data. In practice, it's also good to repeat this process because there's some randomness here, right? So you would randomly pick samples and put them into the folds. But of course, if you redo this, the folds are different. So you get different performance as well. So it's usually good to repeat this process a few times with new folds. Okay. So we have a coffee break now.
Yeah, maybe 5 minutes, if that's okay. Then we continue to the next talk.
Go ahead.
Hello, everyone. Hello. Hi. Welcome back. So, second point of programs today is much more specific to what we do here in CUBRIC. Like the first part was mainly about machine learning in general. And here we invite one of the experts we are happy to have here, Dr. Jiaxiang Zhang, to tell us about what specific difficulties we can face when we want to apply the techniques we discussed to neuroimaging data.
Okay, thanks, Marek. Well, actually, I'll be really happy if I'm really an expert on this field. But I think Matthias already gave us a really nice introduction about all the foundations and issues that you need to know to apply machine learning methods to brain imaging data. So here, I just want to give you a kind of even more brief overview from an end user point of view, how you can use the different type of methods to help us understand the questions that we are interested in. So I changed my title slightly to make it sound more positive, and I hope that is the information that I will give you by the end of my talk, okay? Because it is a very good method, and I think you should consider to use that in your projects or research. Okay, so the one really nice thing about human in vivo brain imaging, as compared to many other tools in neuroscience, is we have the ability to acquire high-dimensional data. And this applies to almost all modalities that we are working here at the CUBRIC. So it's from, for example, human electrophysiology, so that's EEG, MEG data, where when you do scanning, you actually acquire data from multiple electrodes or multiple channels. If you do functional scans, for example, if you do both fMRI or if you do PET, then normally you would acquire information across millions of voxels or tens of thousands of voxels at the same time. This actually also applies to more quantitative MRI or structural scans such as diffusion-weighted imaging, where you actually, again, acquire a large amount of information from multiple modalities. Now, so Matthias already introduced the concept of feature in machine learning. So here, as a brain imaging researcher, so you can easily consider the features as the dimensions of your data, okay? So if you're working on the EEG, MEG data, the feature would normally be a different sensors or different time points of your experiments. If you're working on both fMRI or PET, the feature would not be all the voxels inside of the brain. If you're working on structural image, it is more likely to be the tissue microstructure matrix, again, all over the brain. Now, in most of the experiments, what we normally do is we acquire high-dimensional data and across multiple observations, because the data is noisy and is highly noisy in most of our experiments, okay? And with the hope that we can somehow extract information by averaging or combining observations or multiple observations. And very often our papers or our projects don't just involve one participant, so we very often acquire data in high dimension across multiple observations and including multiple individuals or subjects. So this is the type of data that we are normally working with in brain imaging research. On the other hand, the need or our interest is not that complex, okay? So usually, what the questions that you want to address in all the research is either to make a categorical or correlational inference, okay? Whether there's a difference between conditions or whether any measures from imaging correlates with any metrics or individual traits that you are interested in. In some other cases, you might also want to compare if there's any computational models or if there are any disease that show differences in terms of the data or imaging data that we acquire. In some other cases, and that applies to most of the clinical neuroscience studies here, is when you're working with a clinical population, you might be also interested in either diagnose or prognose of certain clinical populations or certain medical interventions or behavioral interventions, or try to distinguish or detect or predict certain clinical phenotypes. So our interest is actually very simple. Now we have this very kind of interesting scenario. That is, we have all these fancy machines to give us high-dimensional data in one hand, and in the other hand, our needs actually is quite simple. It's either try to distinguish between conditions or try to separate between groups that can be a patient versus controls or patients with different subtype of disease, or we want to assess some results of interventions. And this type of problem, that is, try to start from high-dimensional data and draw a conclusion about very simple differences, is precisely what machine learning can do for you or for us. So following the last talk, the machine learning has very long literature, actually much longer than the human brain imaging. The essence of this community, of this approach, is try to make sense of the data. So here the data normally refers to data sitting in a very high dimension. Okay? And the key point of this is all the classifiers or models, as we heard for now, is trying to extract or seek the information from the high-dimensional feature space. Yeah, remembering the feature refers to anything in our imaging across modalities. The end product of that, after we fit a classifier to our data, is a multivariate decoding model. Okay, or sometimes we refer to this as a discriminative model. What it essentially does is it gives you the probability of information, so the information that you're seeking, which can be difference between conditions, groups, interventions, etc., given the data, the high dimensional data that we have from scanners. Okay, so this is what the machine learning approach can do for us in this decoding approach. And this is very different from the univariate analysis as we heard so far. The univariate analysis has been very successful. It's still dominant in the brain imaging field. The main difference here is rather than try to make sense of the entire data across dimensions or try to seek information across dimensions, the univariate analysis is try to make sense of individual data features. Okay? So normally, if we want to make an inference in our fMRI data using a univariate approach, what we normally do is we take one feature that can be one voxel and look its responses between conditions, between groups, or between interventions. So that is the major difference between the two. And if this is the difference, is the multivariate approach better? Maybe. So here I will just give you a very simple dummy example. I just quickly, easily stimulate a 6 dimensions that contains information. So here information is really arbitrary, so it just means values between condition 1 and condition 2. So among those 6 dimensions, the 4 dimensions actually contains information, meaning that there is a difference in the mean of the value. Okay, so in the dimension, the first dimension in yellow, so there's a difference between condition 1 and condition 2. So that's, I think that's a mean activity in some sense. And there are 2 extra dimensions which have a non-zero means, but they are equal between the 2 conditions, meaning that they don't have information to distinguish between condition 1 and condition 2. So we have the means across the 6 dimensions. Among those 4 contains information. And then I just add a uniformly distributed noise with very large variance. So just to make the data looks like a normal data from scanner, which is a bit crappy. Then I just apply the linear support vector machine as we heard from last talk with 10-fold cross-validations. For each test, I change the number of samples available for training and the test. So with change from 50 samples per condition, so the 100 samples for the entire experiment, up to 500 samples per condition. The last thing I did is I introduced from 0 to 450 noise dimensions. So that is just means the actual dimensions only contains noise, with 0 means and there's no information. Okay, so there's no difference in the means. So if you apply this, you can easily do that. It only takes 20 lines in MATLAB, so it's very straightforward. Then if you test the classification accuracy from the SVM, this is what you get. So here you are seeing the classification accuracy plotted against the change of the samples in each experiment from 100 to, from 50 to 500. And on the y-axis, you are seeing the number of extra dimensions that do not contain information. Okay, so I hope what you can appreciate from here is if you want to achieve high classification accuracy, the easiest thing to do would be to increase the number of samples because that increases the accuracy. At the same time, to decrease the number of noise dimensions. Okay, so you do not want the noise to influence your data. Okay, so even though one of the SVM, probably a common classifier, promised to seek information in high dimensional data, but still in reality, in practical, you want the noise to play as little role as possible in your experiment. Okay, so this is the ideal case. This is what we want to achieve in our experiment. But as many things in our life, we don't always get what we want. Okay, so this is what we get from our data. The first challenge when you apply machine learning methods to bring imaging data you're facing will be you have very limited observations. Okay, so just give you a kind of rough number to think about. When I write a proposal, I always say, okay, I'm going to need 30 participants because sounds about right. And you see tons of papers being published with n less than that. Okay. If you're working on a data set has more than 100 participants, you should consider yourself lucky because it's not that common. If you're working on a data set have 1,000 participants, you consider yourself really lucky because there's handful of paper with that power. So that's the number of subjects. And if you are doing a functional experiment, for 1 hour of functional scans, so either from MAG, EEG, or both fMRI, the best I get is about 700 trials, okay, nothing more. This is given the condition that your subject was not sleeping in the scanner, so you can still use those 700 trials. So this is the amount of data that you can collect from a normal-sized experiment or projects. Now, in contrast, this is probably the state-of-art development in artificial intelligence or machine learning literature. I don't know whether you have heard the Google's DeepMind subdivision developed this AlphaGo algorithm. So this is a kind of deep neural network, which I'll come back to that later. Try to solve a very not simple but straightforward board game showing on the right. So this board only have 19 by 19 grids, okay, and much smaller than the voxels we have in the brain. So in order to achieve superhuman performance in this particular board game, the AlphaGo algorithm actually was trained with 160,000 games. Okay, so that's the number of observations or samples in this particular application. And within each game, there are normally hundreds of moves. So that gives you millions of moves to be able to achieve a good performance. So that is the biggest challenge. That is, you don't have that amount of data to play with. Maybe kind of a good news is actually, as a community, we now start to realize that, and actually you see more and more large sampled cohort-based data become available. So one example is the UK Biobank, with the aim of scanning, I think, 100,000 participants. Although the scans from this particular project, I don't think it will contain a lot of functional data, so it's probably not directly applicable to your research needs. But still, I think the field is moving towards this large sample, high power design. So the limited observations, I really don't think you can do much except you make your design more efficient and try to prevent your subject from sleeping the scanner so that you can get as much data as possible. Now the second challenge is something that you can do something about it, is come back to this feature space. Okay, so I've showed you that although the imaging data normally comes in high dimension, but in order to get meaningful results, sometimes you do not want to work on a very high dimensional space. So the dimensionality from the scanners downstairs, if you're doing MAG, normally give you around 270 channels or sensors or dimensions. If you're working in both fMRI or structural MRI, you're looking about half or 1 million voxels across the brain. Okay, so this is the total dimensionality, if you like, you can play with. In practical, what we normally do is to reduce the dimensionality before apply a classifier. It's just because most of the dimensions, they may just contain noise. So it's not our interest to look all of them. There are many approaches to do that. So here I just highlight a few of those. Maybe we can come back to this during question time in the afternoon to discuss what would be the best way to choose given a particular project. The first, probably very easy way to do it is when you have an a priori hypothesis. Okay, so if you're running a visual experiment, it makes sense that you're only looking at the voxels within the visual cortex. So that's pretty straightforward. So you limit your dimension based on your research questions. The next approach is normally what we call the univariate contrast. Okay, so this refers to, for example, again, if you're running a visual experiment, you want to look at the visual cortex, the voxels in the visual cortex, that actually responds to your stimuli. So what you can do is, before you run your classifier, you select the voxels or data dimensions that actually shows changes or response to the stimuli. And you kind of discard all those voxels which are not very interested in the incoming stimulation or incoming information. So you can use a univariate analysis to prime your data to reduce the dimension for multivariate analysis. The third one, which actually is widely used, is you project your multidimensional data into a new space. So one good example is PCA. Okay, so you can use PCA to project your 100-dimensional data into 10 or 20, which normally those 10 or 20 components already explains 95 or even higher % of variance in the data. The next one is actually coming directly from the machine learning community, is what we call recursive elimination. So here, for example, when you start with, let's say, 4 dimensions in your data set, okay? So you run your classifier across all dimensions, then you find which voxel contributes the least to your result, okay? And then you get rid of that voxel or that dimension. So that leaves you 3 dimensions. Then you do the same thing again. Then you find out among those 3 dimensions, which one contributes the least to the result. Then reduce dimension one step further, give you 2 dimensions. So here you kind of recursively reduce the dimensionality of the data to help you to boost the performance or the decoding performance. The last one is actually coming from the brain imaging community. It's kind of what we normally refer this as a searchlight. So here is when you want to kind of loop through the entire space or entire dimensions you have, and you do not want to lose any dimensions. And this is the one way to go. So again, let's assume you have a total of 4 dimensions, and you limit your multivariate analysis on 2 dimensions. Okay, the way to do it would be you run your analysis in the first 2 dimensions, then you loop it through to the next 2 dimensions, and then it goes forward. Okay, so it's like you have a very small searchlight to go through the high dimensional space, so that once it's finished the search, you get the information pattern across all the dimensions we have in our data. Any questions on that? Okay. Right. So the third challenge, I think, is actually very important, is we already have the problem of choosing all sorts of parameters, the pre-processing or the post-processing for the brain imaging data. The multivariate analysis is actually even worse in this case. You have a much higher researcher degrees of freedom, because now you first need to, let's assume you have done your pre-processing, okay? Then you need to choose which features to go into the classifier, which classifiers to use, okay? Which algorithm you want to use. And even though you settled on a particular classifier, normally there are many parameters for that classifier you can tweak. Okay, so you need to set the value of the parameters. So basically, there's a huge number of combinations you can play with, and that's kind of a bit unsettled for a given particular project. The kind of a problem related to that is there's no kind of one-size-fits-all approach. There's no a single classifier that guarantees to give you the best result across all the projects. So here, just give you a very simple example. It's a very small data set called ionosphere from UCL. It doesn't matter, it's not an imaging data set, but it contains about 350 samples, observations, 34 dimensions, and 2 classes, 2 labels. So here, what you are seeing here are the area under the ROC curve, as Matthias nicely explained. So basically what you're looking here is how good, basically it's a performance measure, a metric of a classifier, which is unbiased to unbalanced class numbers, okay? So anything above 0.5 means the classifier performance is above chance, and anything reach 1 means it's a perfect classification. So what you can see here is that it's the same data set. I didn't play with any parameters in any given classifier. But what you can see is there's a huge difference among those commonly used classifiers. So the first one is a decision tree. Second one, the support vector machine, logistic regression. This is a neural network with backpropagation and naive Bayes. Okay? So the area under the ROC curve varies between about 85 to 93%. Okay, so that's a huge. It's like a 10% variability. Okay, if you think your data sitting on the kind of borderline of being significant, okay, if it's a binary classification, you're looking about 50% accuracy. Then by changing to a different classifier, sometimes it will change between 45% to 55. That means you change from not significant to significant results. So it is a problem, and one way to address this problem is come back to the one issue that raised in the last talk is we leave a test site that is independent of what you're going to do with the training set. So here you can, one way to do it would be you can take all the parameters, all the features, and all the parameters, okay, in one training set and leave your test set intact. And by the time you say, okay, I had enough playing with those classifiers, then you test your result into a new independent test set. So this is one way to address that. If you have a better way to do this, please let me know, because I'm also interested in how to do this in a better way. So another way that somehow can control or kind of give you some heuristic about choosing all those methods or parameters is to be clear what you want for your research questions, okay? Because very often, different research questions impose different needs. So if your project is about cognitive neuroscience, you want to understand how the brain operates or what computation is performed in a particular task, you may want to use a classifier that gives you a more direct interpretation. Okay? By that, I mean it's probably easier to use a linear classifier, okay? Because the information that you get from the classifier, you can map onto the importance of the dimensions. So I come back to that later. If your project is to try to predict or try to diagnose the clinical population or try to distinguish clinical phenotypes, in this case, then the classification performance might be the most important metric you should be looking at. Yeah? You don't need to care about how easy to interpret the classifiers. Here, the most important thing is, can you find the classifier give you the best true positive and the least true negative? Okay? And the last thing is, again, we see some new application in this area is if you want to develop, for example, a real-time neurofeedback or real-time brain-computer interface, or even something like the cognitive neuroprosthetics. So here, the speed becomes more important. So you want real-time speed, you want real-time feedback, as opposed to the neural network, which probably takes hours or at least minutes to train. So be clear with your research needs and sometimes help you to choose which methods you can use. Right, okay, so that's probably the challenges I think we should consider when we run or apply the machine learning methods to imaging data. And there are a few things I think be useful to pay attention, really, when we have the results, okay? One common kind of conclusion that you see from papers, applying classifier is they all claim, including some of my previous work, I always say the machine learning approach is more sensitive. Because sometimes it makes sense. You're looking at data from high dimension, and sometimes you get significant results when the univariate analysis doesn't give you. So now my take on this is maybe it is more sensitive if the information of interest sits in high dimensional space. So what it means is if your research question is more direct, for example, you want to test whether the posterior caudate have a different activity between Parkinson patients and controls. You do not need a classifier, okay? Because you actually can just do a standard univariate analysis that fits perfectly to your inference. And also, even though sometimes the machine learning approach gives you significant results where the univariate analysis can't, this is not a free lunch, okay? So actually, you lose the specificity in the feature space to make such conclusion. So here, just give you a very simple example. So on the left, when you have a univariate analysis, okay, let's say feature 1, feature 2, or voxel 1, voxel 2, sensor 1, sensor 2, doesn't matter, between patient and controls, okay? In the univariate analysis, if you observe a significant changes or effect in feature 1, not in feature 2, or even better, if you see an interaction between the two, you can directly make an inference that the effect you are looking for is in feature 1. Yeah? There's no doubt. It's very clear. On the right is what you normally see from multivariate pattern analysis. That is, okay, the data is more noisy, the information content is smaller, therefore, in the first dimension, there's a little bit deactivation in the patient group. In the second dimension, there's a bit overactivation in the patient group. Both are not significant, but if you plug this type of data into a classifier, very often you will see significant classification because now from a higher dimensional space, this pattern can be separated easily. So your conclusion will be, okay, there is some difference between patient and controls. At a cost, now you lose the specificity across the feature space. You cannot easily say the feature 1 versus feature 2, what happens between the two groups. So this is something which I refer to the over-optimism. People normally use the classifier and their results blindly to the potential inference that they can actually be made. Okay, second thing is overinterpretation. So that's another danger that people sometimes will encounter. So we may overinterpret the method itself. Okay, you will see all these headlines that okay, so there's some new paper claim, scientists from CUBRIC find a method to read the mind in some way. Okay, in some projects that is true. Okay, but this is not always true. Okay, the machine learning, it is not equivalent to mind reading. From the other side, you do not need machine learning to read the mind. Okay, I'll give you a very simple example. Think about motor imagery. Okay, if you ask your patient to think about the sports, you will see increased body response in scanner, in pre-SMA or premotor. Okay, there's no question for that. And that you do not need a classifier to tell you they are thinking about sports. The second is probably more kind of relevant to us, or how we put in a conclusion in our papers. Sometimes you see a significant classification in some area being referred as this area is responsible for neuronal coding. Okay. Again, please be aware this may not be true. Okay, so what you see, okay, when you have a significant classification performance from a region of brain, what it really tells you is the multivariate patterns that you have. Okay, either from fMRI, from MAG, from EEG, they contain discriminative power to the question that you're looking for. Okay, so it is only in the feature space that has a discriminative power. It does not necessarily mean the underlying neuronal coding can be described. Okay, because the reason is what you see, the result is actually can be a hybrid of the true neuronal coding, the things that you want to infer to, plus the sampling. Okay, so in both fMRI that could be local vascular changes, and noise. And in this paper from 2014 actually shows probably the most benefit we get from the machine learning approach to brain imaging data comes from denoise to the irrelevant dimensions, as opposed to being more sensitive to informative dimensions. So if you're interested, I highly recommend you to read this paper. And the other side, you should also pay attention. That is, when you do not see a significant performance, it does not necessarily mean there's no neuronal coding in that area. It just means our method is still not sensitive enough to pick out what we want. All right. We have already heard the topic about overfitting. And this is not limited to machine learning approach alone. So you probably all heard the term double dipping from the last few years. And that, again, does not only apply to imaging community, but also applies to psychology, biology, neuroscience, all the areas. But when you apply machine learning approach to brain imaging data, it is potentially dangerous, partly because we have such a long analysis pipeline, yeah, as I mentioned before. After your pre-processing, your analysis just begins. Okay, then you have to deal with the feature selection, the selection of classifiers, selection of parameters. Along those steps, you really should be paying attention to avoid the potential of overfitting. Okay, the best approach, really, as I mentioned before, is to leave your test site aside. Okay, so store that in another folder, okay, or to another drive, or give to another person in your lab. Don't see your test site. And you can play all the tricks in your training set and test that in independent data samples. Just to show you how bad this can be, remember our dummy example from all the parameters that we nicely set out here, give you a change of accuracy over samples and noisy dimensions. So here, just pick, I can't remember which one, sorry. I pick any one parameter segment here. It's probably around 100 samples per conditions and maybe 100 dimensions. So if there's no overfitting in my data, if my classifier does not see any of the test sample during training, this is the true classification performance. Okay, so it's about 60% accuracy, so just a little bit above chance. So here what you're seeing is the classification accuracy plot against the proportion of test samples that spilled over to the training of the classifier. Okay, so this means no sample being spilled over, 20%, 40%, 60, 80, and 100%. So what you can see here is, even though you may only, by accident, leak 20% of the of the samples to the training process, you immediately boost your classification accuracy. Okay, so this is what we call overfitting, or double dipping, because you actually, so here the classification accuracy does not reflect the true predictive power anymore. Okay, and it's all got inflated heavily all the way up to 100%. Right. The last point is the classification weight. So come back to if your question is about cognitive neuroscience, as I recommended before, it's probably easier to use a linear classifier because you can directly interpret the contribution of the weights of each dimensions. This can be done by looking the weight of the classifier. This applies to both SVM or LDAs or many other linear classifiers. That is, if you see the weights of each feature dimensions, it tells you the importance of each dimension contribute to the classifier, to the classification problem. Okay? And the problem of that is it is not straightforward to only look that feature alone. Okay, so the feature is important to the classification, does not necessarily mean the feature itself contains information. Okay, John Dylan Haynes has a very nice example in his 2015 paper. Shows you. So imagine there are two voxels, okay, in the brain. The one contains very low amount of noise, have some sort of noise. Very low amount of information embedded in some noise. Okay, this is voxel 1. And another voxel contains purely noise. There's no information, but the noise profile is identical to the informative voxel, which has a little bit of information. So purely noise plus little bit information. Okay. Now, if you subtract the purely noisy voxel from the activity of that, from the activity from the voxel 1, which contains a low noise, what you get is, because subtract out the noise, what you get is a observations is high information. Okay, and this more or less is some classifiers do. Okay, so it denoise the information in the data by taking into account the dimension that only have noise. Okay, so now let's assume this is output of the classifier, because with high information it's very easy to see the difference or the interest of the classification problem. If you try to look how to check the classification weights, both voxels should have a positive weight, non-zero weight, okay? Because both contribute to the classification result. But if you only look the voxel with purely noise, it doesn't contain information. As yet, it has a non-zero weight because it contributes to the classification problem. Okay, so that's enough about negativity. I think I'm running over time. So in the last 5 minutes, yes?
That example you just gave, isn't the key issue there that the two features are actually correlated? Because the noise in one is the same as the noise in the other. So
but yes,
yeah, so they're not orthogonal features, is that?
Yeah, but we normally don't. People normally don't care about that. So they normally interpret the weight naively or straightforward.
Okay.
We shouldn't really. But there's a way to work around of that. Try to look this paper from 2014. They propose a method how to deal with this. It's not a perfect solution, but it's a workaround. Okay, so now move on to the positive kind of side. There's a few kind of changing trends happening in the last few years now, which actually moves away all the things I've been told you before. Okay, the one thing is that if you think about all the problems I've discussed so far, it goes one way. Okay, so you have a high dimensional data, then you try to decode some simple classification questions. You can turn the tables around. Okay, so rather than doing decoding, okay, you can directly go into encoding model. Okay, so here is when you have a very clear hypothesis, okay, very clear model, forward model, then actually what you can do is you can predict what the high dimensional data would look like, and then try to correlate the predicted data versus the measured data to see whether your assumption is correct or not. And this is particularly useful if your question is not that simple, okay, patient versus controls, or condition 1 versus condition 2. So if you have a much more complex problem, the encoding approach could be better. Here, just give you one example from Jack Gallen's lab from UC Berkeley. So now it's almost 10 years old, this paper now. So basically, it's not new anymore. What they do in this particular example is first they present a bunch of pictures to the brain, okay, to participants in fMRI, okay? And what they do is for every single voxels in the visual cortex, okay, they estimate the receptor field model. Okay, so this is type of model given the input of image, so that's where you get the gray scale intensity and edges and all the different low-level features to estimate what is the receptor field of this particular voxel in the visual cortex. And once you identify the receptor field of this particular voxel, then you look their tuning profile in the orientation and the spatial space. Okay, so here you get complete encoding model. That is, you know exactly how the response of this voxel would be, or the best fit of this voxel's response would be, if there is information or if their stimuli falls into the receptor field of this voxel. Okay, so this is their encoding model. Once they have done that, they present participants a new bunch of stimuli, and so here again you have a measured boulder response from exactly the same voxel. But now, because you have this encoding model, you can predict what this voxel's activity would be if this model is true. Okay? Now we have the predicted and measured boulder response. You can just correlate the two, then you get a very nice correlation. Basically shows that the model is correct. The model itself has very good predictive power to the boulder response. So I'm just going to go speed up. The next thing that we can try to improve the interpretability is to move from classification to the representational similarity analysis, or in short for RSA. So please read this paper from Nico Chris Cortes, because this introduces very nicely what this method is about. But in one sentence, it refers to the very simple assumption that is, if information is similar, okay, then their representation in the brain should also be similar. If the information is not similar, if they are dissimilar with each other, then their representation should also be distant apart. So this is a very simple assumption, and normally it holds. The assumption gives you the power to link the different computational models, okay? Because the similarity of information is purely determined by your hypothesis, okay? If I think there is a region of brain has similar information of all the animate stimuli versus inanimate stimuli, then I can, construct a model to capture that similarity structure. Okay? If my model says, okay, this brain region actually is not about animate versus inanimate stimuli, it's about phases versus non-phases. Okay? Then the information content will change. Depends on the model or assumption that I made. Okay? So that offers you a way to directly test model-based predictions at a more kind of abstract level. So you are not trying to seek one-to-one correspondence between your experiment conditions and bold or map response. Rather, you are trying to seek correspondence of information representation from model and information representation from the data. And also, because you're looking the correspondence of the information, you can easily compare data across modalities. Okay, so here in this paper, it just shows you can easily do that to compare the monkey inferior temporal cortex and the human IT area within the same task, actually, and the information content across modalities and across species. Okay, so I'm really over time, but I really want to mention this because I think this is really exciting. So just bear with me with 1 second. I made this slide yesterday, just before the dinner. So this reflects my little understanding of the recent trend in deep learning. Okay, so really, I talked to you about a few ways to improve the interpretability with some new methods, but also there is a kind of rapid change in the machine learning literature community trying to improve the encodability or decodability of all the algorithms. One good example is deep learning. Okay, so if you can just think deep learning is an extension of the already dead artificial neural network, but with more layers of good stuff. Okay, so that's enough, I guess, for now. This allows you to remember I told you the mapping between high-dimensional data and easy, kind of naive sometimes the research question we want to look. So this allows you to map high-dimensional data to high-dimensional hypothesis. Okay, so here just give you one example from Fei Li in Stanford. So basically, what they do is try to map the text description versus picture. Okay, so I don't want to go into detail, but essentially the end product is a generative model that is to train the network, the deep neural network, to learn the mapping between image elements, so cat, laptop, phones, tables, to a word description. Once the network has learned this very complex mapping, when you present a new image to the model, it can automatically generate a text description based on the features that it learned and the mapping that it learns between the text and the image. So here it's a text image like this. Can you see that? So basically it just says the tabby cat is sleeping on a wooden desk beside a shiny laptop, something like that. Okay? I think although those kind of changes still happen just in the AI or machine learning community, but I think there's huge potential. We can use that to address some very difficult problems we are facing in brain imaging. Okay, so last slide really. As I've told you about the necessity really to look the high-dimensional brain data by using the machine learning approach. And there are also some really promising trends. One way is to improve the interpretability by using encoding models or RSA. The other, I think, actually it's also very exciting, is to improve the encodability or decodability by using deep learning or deep neural network. And hopefully, someday, we will have a fully generative model with superior interpretability and superior encodability. I'll skip that. This is a really cool paper just coming from last month in Science. They claim they use basically a biologically informed deep neural network. It's not deep neural, biologically informed multi-layer network to crack the captures. So those are the images you normally see when the website try to verify you are human, not a robot. Now the algorithm can do that. It's almost as good as human. Okay. All right. So this is discussion, and the first point is obvious. The second point, I think, is really useful to think the emphasis on information because it goes beyond the simple decoding of the conditions, but allow us to validate models and also to integrate between modalities. And also, it's very exciting time because now we're at the new development of neuroscience, but also from AI. That's all the papers. Okay, thank you.
Yeah, so we have time for two or one questions. So, anyone? If not, oh yes.
one question related also to Chris's question with the correlation between features. You mentioned a few techniques to reduce the feature space. So just referring to your last slide, do you see a possibility for combining the deep neural nets with something like RSA, where you take into account the autocorrelation between your features, and you make use of a neural network, and then you read out the weights from your network and try to...
Yeah, you can. But normally I think, feature selection as kind of one small step of pre-processing before you actually apply all the standard methods. And this actually is similar to what they did in this paper. So here they only feed the network about 1,400 images, and those 1,400 images are taken from, if you like, it's a sample of about 20,000 ish, so more images. So they're taking the images that are more representative to train the model. Okay, so the feature there's really many ways you can select the best feature. The problem is, if you end up with only one feature, which is the most representative, then you might just do the univariate analysis, right? That probably should give you as good performance as it can be. Yeah.
But in principle, it might be, if you take into account the correlation between features, in principle, you could possibly combine the two approaches to preserve interpretability and have optimal encoding performance.
I think actually that's why some people do PCA before the classification, because if you have 1,000 voxels in an area, you're probably looking at 40, 50 PCA principal components, which explains most of the variance. That kind of sometimes explain or take into account the correlations between dimensions.
Okay, any more questions? If not, well, so let's have a 10 minutes break, and after 10 minutes, we meet again here.
Thanks, Jiaxiang. This was really great.
Yes, very useful.
Should we just stop? Yes, please.